So, good morning, everyone. My name is Konstantinos Politakos, and I'm a research assistant at the Remote Sensing Lab of Forth. Today, I will talk through a project that brings together remote sensing and flux observations to evaluate urban CO2 emissions, specifically heating emissions, modeled by ECMWF, and assessed through eddy covariance flux measurements in Iraq and Greece. This work was carried out as part of the CoCO2 project. Now, I know that many of you are experts in remote sensing, but eddy covariance might be a new territory. So, essentially, the goal was to build and test prototype systems of the CO2 MVS that will operate under Copernicus. What made this project powerful was scale and collaboration. As you can see on the right, there were many research infrastructure, laboratories, and universities that actually collaborate within this project. Together, the project delivered tools to estimate emission from global to city level. Now we'll see a few key objectives of the project. First was to deliver prototype systems for estimating anthropogenic CO2 emissions, like the MENDI that we'll talk later on. Second, to engage this with users, with scientists, policymakers, and service providers to make sure that the systems being developed are actually fit for purpose. The third one, the understanding and quantifying the uncertainties. And fourth, the system provides early inputs to first global goal state. And finally, to support the operational implementation of this system. So now some key deliverables through this project. As you can see, here's a concept figure showing how we can split the overall process of satellite-based CO2 monitoring into components. Here we have deliverable 5.5, showing how sensitive the model outputs were, particularly for road transport emissions, to different assumptions, and as well as the total CO2 emissions from the CoCO2 inventory on the left, and on the right, the standard deviation on those estimates when the input parameters were perturbed. Also, we have a collaboration with AGH University of Krakow, where we had they delivered measurements through tethered balloons and drones in order to have vertical observations of crucial GHG concentrations like CO2 and methane in order to help and support the inversion modeling. Now we'll take with me the 0.5 in order to talk a bit about the WEkEO. So what it makes this powerful is that the satellite and model-based information is integrated in one place and make it easier to combine data sets and support downstream services. Within this was also the CoCO2 project, which was built on the wealth of the Copernicus data. Here in Iraq and Forth, we also had the ERC Synergy Grant, Herbisphere, which also focused on understanding the feedback between urban transformation and climate change. And last but not least, we recently have joined we are leading the CLMS Seeds program, which is the extent of Copernicus land monitoring service into urban applications, especially those involving greenhouse gas inventories and city smart planning. So now, the two deliverables that we used, our flagship observation was deliverable 7.10, using both flux measurements and modeling approaches, which include the eddy covariance data and flux footprint modeling that I will talk later on specifically, and the composition into source components like traffic, heating emissions, and vegetations. And on the right, the deliverable that I will talk today is deliverable 3.2. Which include the models like MENDI and how to better align models with ground-based observations. So now let's see how the model of ECMWF MENDI actually worked. Through task 3.2, a residential CO2 emission model that operates within the IFS, the integrated forecasting system, and focused specifically on heating emissions from in situ fuel combustion. Three main recommendations of this model was the use of the method within an urban scene. We'll see this later, specifically for Iraklon case study. The extending of the monitoring network. That's why we used our EkEO flux towers along the study. And the third point that I will not focus on this speech is the use of point source emissions directly on the IFS grid. So what was actually delivered by mainly was the implementation of an urban canopy model, which perfectly aligned with Iraklon city, and then later was implemented through the IFS camps and the IFS Menti model in order to get a final CO2 heating map, CO2 heating emissions map. As you can see, in the middle is concentrates the buildings and the residences of Iraklon. That's why we see higher heating emissions through the city center. And how did this model actually work? Meant start from nationally reported annual residential emissions, and then spatially and temporally disaggregates them based on urban land cover and soil temperature. Around 20% of emissions are assumed constant, and the remaining 80% are linked to space heating demand, which is modeled using topsoil temperature. The threshold for the heating these days was set up to 15.5. So now we'll just talk about how we use flux observations within an urban landscape. This is the equation that actually we use when we're talking about the urban flux measurements. VFC is the total net CO2 flux that we meet in a city, and it consists of emissions from traffic, which consists of buses, trucks, or vehicles. Also, some building emissions, which consists of heating emissions from fuel combustion. And of course, the human metabolic CO2 release, the soil respiration, the plant respiration, and the only term which actually has a minus sign is the photosynthetic CO2 uptake. It actually absorbs the CO2 from the atmosphere. So now we have here the Iraklon case study. If you follow the red line, you start from Greece, you go to Crete and then to Iraklon. Here in Iraklon, we operate two flux towers, HECOR and HECMAS. The one on top is HECOR and operates from 2A16, the city center of Iraklon, and HECMAS, a second one in the residential area of Mastabas in Iraklon. What's important to mention here is these colorful areas. So you see a detailed satellite view of the city with modeled flux footprints, which I'm going to analyze later. These show the dominant source areas from each tower under prevailing wind conditions. These two flux footprint areas come through annual datasets, so we can see that we have a strong influence from the northern and the southern parts of the location of each tower. So I'm gonna grab the HECOR images, and I'll just continue on the EkEO variance method and how it's used through the urban landscape. EkEO variance is the only direct measurement technique that captures the vertical exchange of heated mass like CO2 between Earth's surface and atmosphere. You see here that the instruments are actually placed within the inertial sublayer and not in the roughness one. That's why the roughness sublayer is influenced by individual building and trees, while the inertial sublayer above that is where we can measure fluxes that represent the aggregate signal from the surface. So that brings us to the concept of the flux footprint, the upwind area that contributes most to the measured flux. The extent and the shape of the footprint varies from wind speed, wind direction, and surface roughness, which help to determine which is the key to identifying and interpreting different emission sources, like heating, traffic, or human respiration. However, interpreting all these sources is really difficult through the complex urban areas. So on the left images, you can see on the top, the sensor is mounted above the urban surface. The source area is in the perfect cycle. It's shaped by wind direction and turbulence. And on the bottom, we see the footprint stresses in the downwind direction depending on atmospheric stability. Understanding this is really crucial. That's why I have to mention all this methodology, because it tells us what part of the urban surface we're comparing with the model, with the Mendy model, and how will this grid cell align with the flux footprint. So here is once again the image of the HECOR as it's operational till today. You see on the bottom right image that this is a 17 meters high building, and of the roof of the building we have established a 10-meter mast, and at the top of the mast there is the irrigation, the gas analyzer that measures the CO2 fluxes. Okay, now on the left we see high resolution land cover classification over Heraklion, including building roads, vegetation, and bare surfaces. This work based on a recent published paper by Stavsagakis by 2019. The white contour lines represent the model source area of the tower for a year. This is why I told you before that this is annual measurements, and this shows the high influence that we have from northern and southern direction winds. And if we take a closer look to let's say to a 30-minute measurements, we see that. So on the left, we see a high resolution land cover classification over Heraklion, including building roads, vegetation, and bare surfaces. This is based on work by Stavsagakis at 2019. The wind control lines represent the model source area of the tower for a year, and the footprint that contributes most to the flux signal. That's why I would like to focus. I cannot control the on a 30-minute measurement, which actually is strongly influenced by only northern winds. So when we get an annual flux observation dataset, we see that we have strong influence from the northern and south part, and we know actually the main source area of our measurements. So in this project, we also have the help of and assistance of the ICOS associate flux tower from Basel. Basel is a city in Switzerland, and we use the flat footprints from this city in accordance with the model MEGDI, once again, where we can see the high influence of the heating needs from the residents throughout the year. That's really normal, since the Switzerland is much northern than Heraklion, so we can see greater heating emissions throughout the year. So let's see the final evaluation of our model. Now we can return to Heraklion, this time showing how we aligned our measured CO2 fluxes with the Mendy model outputs. On the right, you see a land cover map of the city, which includes building, roads, and vegetation and water for modeling and interpreting urban emissions. So as a quick reminder, I'd just like to say that models and observations may speak different languages. It's important to align sector spatial coverage and units. To make comparisons meaningful, we collaborate with ECMWF, who provided downscale mainly output for Heraklion and Basel at 1 square kilometer resolution. And next, why we selected HECMAS Tower in the residential district of Mastabas and why not HECOR? HECOR is dominated by traffic and commercial activity. Over 7% of CO2 flux which come from traffic alone. And so also the Basel towers are also near roads and commercial areas. In contrast, HECMAS is mainly influenced by residential heating. It's a quiet neighborhood with dense housing and modest traffic. We focused on the winter season from December 2021 to April 2022, when heating demand peaks. We compare the daily Mendy model heating emissions with eddy-covariance observed CO2 fluxes. So that's why you see through the evaluation that this the blue line corresponds to eddy covariance measurements, and these peaks are the total flux through the weekdays. So we see how, the change between the resident behavior through the weekdays and through the weekend. That's why there is a dramatic decline, a significant decline through the weekends, through the Saturdays and Sundays, where the commuters do not accumulate in the center. So this validates the usefulness of HECMAS in capturing real-world heating patterns and supports the Mendy model's effectiveness when sectorally disaggregated and spatially downscaled. You see that during the winter months, December, January, February, March, and April, we have high impact due to heating emissions, and this comes with great correlation with the Mendy model through the ATD correlation. And then we end up with monthly medians to end up with a linear regression and R square of 96%. Still, we must remember that eddy covariance includes more than just heating. It sees everything in the footprint, from traffic to respiration. That's why such careful site selection, footprint massing, and unit harmonization are vital. And now the last slide, just to wrap up. Okay. Urban eddy covariance offers insight into CO2 emissions, but it requires careful interpretation while model alignment. With Mendy, context, and footprint modeling, we bridge this gap between observations and simulations. And while challenges remain strong seasonal correlation, we found remind us that meaningful progress is possible. Last but not least, next slide. Okay, if you want to go fast, go alone. If you want to go far, go together. I have to acknowledge Aura Lupascu, Joy McNorton, Margarita Hulga, Gian Paolo Balsamo, Mark Guevara, Hugo Denvier, Stavros Agakin, Christos Thomas Kaminski, and Marcus Schulze for supporting me through all this research. Thank you very much. I'm sorry for this Zoom thing. I didn't know what happened. I'm here for your questions.
Thanks a lot, Konstantinos, for your presentation. So no worries about the technical issue. It's not a big deal, and it happens often. So for the question, we have a few for you. The first one being, besides the wind direction, what other technical factors do you take into account?
Yeah, that's a great question. I didn't mention it a lot because talking about eddy covariance, it's within the urban landscape, it's a really huge chapter. But for starters, let's say that we also need a surface model in order to see the elevation and to see how our city is structured. We need a digital surface model. And we also need the building height in order to see the roughness that it's created upon all the materials in the roughness sublayer, as I explained earlier. So yes, you will mainly need the building heights, the vegetation, the trees heights.
Okay, Okay, thanks a lot for the explanation. We will go to the next question. How will the CO2 project and the CO2M satellite mission improve the accuracy of global carbon emission monitoring and support climate policy decisions?
Yes, that's a really good question. I'm actually not such an expert on the on how to improve the accuracy, but there's a great context through the CoCO2 website for such satellite specialized questions. I'm sorry for that.
Okay, thanks a lot. The link of the project was also put on the chat, but yeah, we can have a look. Thanks. Okay, can this model be used to detect emissions in rural areas and or the agricultural
Yeah,
sector?
that's a really good question. You see, you see within the urban sim that was created by the ECNWF was mainly focused on. There's also a paper that I have introduced through my presentation. For now, I'm not aware if there is something especially for rural areas because if you can see, we actually focused on heating emissions, anthropogenic emissions for heating. So I don't know if ECNWF have implemented something new for CO2 emissions through the rural areas.
Okay, thanks. Maybe something in the future. Okay. Next question. How does atmospheric turbulence affect the accuracy of CO2 flux measurements in residential areas?
We have, if I am getting this question right, we have to distinguish the scales that we're talking about. You see, when we're using all these CO2 flux measurements, we're talking about local scale. We're talking about 50 to 60 meters above the ground. We cannot upscale this the measurement that we take that we measure through our flux towers with the turbulence that it's going on the higher layers of atmosphere. So their local scales, they are the total CO2 fluxes within a context, a flux footprint area, 1 by 1 kilometer. So there's no high influence from the higher scales of the higher levels of atmosphere. But if you talk mainly for urban scale and below the 60 meters, you may understand that there are skyscrapers, there are all these buildings, there are the trees that actually interfere and affect the turbulence and how the CO2 flux are measured within the urban setting.
Okay, thanks. And yeah, it's kind of the same question next about how can machine learning and modeling can improve.
Yeah, you see, there are two main contexts. The first one that we are also working here, it's the gap filling. You see, there are a lot of maintenances, there are some bad values, there are so many single strengths that we use in diagnostics. So we may miss some measurements. There, the machine learning can actually gap fill a lot of missing values. And except for that, what we can see is that in some cases we can forecast the CO2 flux observations using machine learning, since we have a similar wind conditions and similar traffic emissions, building emissions. So we can forecast, we can foresee what we actually waiting to see from our measurements.
Okay, thanks a lot. And now we will go to the last question for you for today. How does the Copernicus CO2 project leverage satellite data and modeling to enhance the verification of anthropogenic CO2 emissions?
From this deliverable, you see that within the work package 7 of this project, we had this deliverable made by the by the flux towers that we have here in Heraklion, so we could implement our flux measurements, these local scale measurements with IFS, which is a global model, first of all. And second of all, we had the measurement from Krakow, from AGH University, which I talked at the beginning of my speech, where when you're measuring the vertical profile of CO2 and methane, you can better understand how to use them as validation to your inversion modeling.